Now, in this session, finish off trying to find the inverse of a permutation, where the permutation is expressed as a product of transpositions. Right? So here we've got five transpositions. Remember, transposition is just a cycle of length 2. Okay? And transpositions play a rather special role in finite group theory, as you'll learn if you go to higher levels. All right. So you're given this permutation. It's expressed in terms of 5 transpositions, and you're asked to find the inverse of this. So how do you go about doing that? Well, if it were in the standard bracket form, you know how to do that. But how do you do it when it's in this form as a product of transpositions? How do you do that? Well, we need a bit of theory. So now maybe this is a bit of revision to you from more elementary group theory, but if it's new to you, then you'll need to know it. So what is the inverse? Now, we're just talking ordinary group theory right now. These are just ordinary elements. A and B are just ordinary elements of a group. And you take the binary product of 2 of them, and we're talking multiplicative use. So we just use a shorthand. Instead of saying A binary operator B, we just say AB. So what's the formula for the inverse of AB? Now it's B inverse A inverse. So I'll prove that here if you've not seen this before. Probably you have, but anyway. So in words, you can say that the inverse of the product is equal to the product of the inverses reversed. Right? So he got AB, he got BA. So the inverse of the product equals the product of the inverses reversed. Okay. Now, how to prove that? Well, we don't know what this is. It'll be some element of the group, right? It has to be, because it's closed. So AB will give you some element of the group, and whatever that is, the inverse of that result, that product, will belong to the group. Okay. So whatever it is, whatever this is, let it be C, and let's try to prove that C equals this, and therefore this equals this. So let's try to find what C equals. Okay, so we let C be equal to this. So that's what we have here. Now, post multiply on both sides, in other words on the right-hand side, on both sides by AB. Now, why do that? Because the right-hand side will then cancel, become E. Okay, so C of AB is this times AB. Now this is just the inverse of that. Okay, so it's just E. That's the property of the inverse. A bit of revision going back quite a few lectures to standard group theory. Right. Okay, so you've got CAB cab is equal to E. Right, now post multiply on both sides here and here by B inverse. And why do that? Well, because you get rid of this B here. So you get CAB B inverse is E B inverse, both sides same thing, okay? And this here, the B inverse becomes E, so this just becomes CA, so this is this, okay? And E times anything is just anything, so this becomes this, right? Okay, now post multiply by A inverse here and here, and so CA A inverse becomes B inverse A inverse, right? The A inverse, in a sense, cancel. That just becomes E. So this becomes CE, which is just C. But what is C? C is this, okay? So, in other words, this and this are equal. All these things on this line are equal. So that and that are equal. And therefore, the inverse of the product is equal to the product of the inverses reversed. Okay, so we've proved this. All right. Now you can generalize that. I don't do it, but you can do that as a homework exercise if you like. Now what is the inverse of a triple product ABC here? Well, it's sort of similar, except this extra term you'll have the inverse of it. Its inverse will then be on the left, and so on. Now, okay, so let's generalize this to like n terms. In this case, 5 terms. So if you want to find the inverse of this, it will be this one's inverse on the left side here. Right? Then the inverse of this here, like to the right of it, and then the inverse of this to the right of that, and so on. The inverse of this here, inverse of here. Now, notice the order of these: 4, 5, 2, 3, 4, 5, 2, 3. So going that way, and it's going this way. So it's the product of the inverses, but everything's reversed. Okay. Now, remember, just at the end of the previous session, showed that the inverse of a transposition is itself. Okay? So what is the inverse of 4, 5? Well, it'll just be 4, 5. Right? The inverse of a transposition, so see this is a cycle of length 2, by definition it's transposition. So the inverse of a transposition is just itself. So instead of writing 4, 5, the inverse of that, well, it's just 4, 5, the cycle. And similarly for the others, right? So in other words, you just get rid of all these inverse signs. Right? And there it is. There's your answer. There's your x inverse. That's the inverse of that permutation. Right? The inverse of this is this. All right. Now, can you remember from the previous session that when you find you start with a permutation, and you knock it down, you decompose it, if you like, into a product of transpositions, these cycles of order of length 2. You can do that in various ways. So you get different answers, right? You have a different product of transpositions. It doesn't come out uniquely. I mean, you get, by using different methods, you get different answers. But something's interesting if you notice this. Say you have a given permutation, and you break it down into products of plural products of transpositions. You get different products. So you have a list of them, different products. Now, interestingly, the number, or I'll put it this way. If you look at each of those products of transpositions, they will either be all even, meaning an even number of transpositions, or they will all have an odd number of transpositions. Interesting. Yeah? So this is when you're a pure mathematician, you're exploring this kind of stuff, and you're sniffing around, and you notice these patterns, right? As Marcus de Salto keeps saying. I mean, this is part of the fun of being a pure mathematician. You play with this stuff, and you notice these generalizations, and that gives you clues on a future theorem, right? That may motivate you to think, well, there's a pattern going on. There's some sort of commonality, something in common is happening here. What is it? So you start thinking about it, and so on. Right. Okay, moving on a little bit. So I'll leave that hanging for a while, because the theorems coming now will elucidate this, help see why that's the case. All right. Question: If you take a transposition, it's just a transposition is a very special kind of permutation, right? All it does is just swap two of your members of the objects that you're permuting. It just swaps two of them and leaves everything else the same. So in a sense, if you're if this like is like the set of objects that you're permuting, and just put them in a line, for example, and So you have two lines in effect, and this second line is the line of objects that result from your permutation. Now, if it's a transposition, you're just swapping two objects. This is a cycle of order 2. It's transposition, right? So in effect, all it's doing is just swapping R for S, right? R becomes S and S becomes R. So you get R becomes, gets swapped to this position where S was, and S gets swapped to where R was. So R becomes S, S becomes R, and all the others, no change, right? So a transposition is just a special kind of permutation. Now, permutations, you remember from earlier, are of two kinds, two families. They are either even or they're odd. And remember what that means, bit of revision. An even permutation, that's the number, that means that the number of its reversed pairs is even. And a permutation is odd if the number of its reversed pairs is odd. Now, earlier we showed that the number of reverse pairs is equal to the number of cross points when you, like here's your starting configuration of the group of the set of objects that you're permuting. So if you line them up here, and then you have a similar line of your objects, but after the permutation, and then you just draw straight lines between objects of the same name, same ID. So you go 1 to 1, 2 to 2, whatever. Now for a transposition, nearly all of them will just be vertical lines. No change, with the exception of these two objects get swapped, right? Now we can figure out. Now that's a general case for a transposition, right? You're just swapping two of the two objects in your set of objects that you're permuting in general. Now the number of cross points is equal. That was one of the theorems. The number of cross points is equal to the number of reversed pairs. Okay, and the number of reversed pairs, if that's odd or even, it means by definition it means the permutation is odd or even, right? So let's try and prove. You can probably see it here visually. Let's try and prove that any transposition is odd. You see, a transposition is a permutation, and permutations are either even or odd. So a transposition, if transposition is a permutation, and permutations are even or odd, therefore a transposition must be even or odd. Okay, follow that logic? So which is it? Is a transposition? It's either one or the other, right? It's just one permutation. That's a transposition is just one permutation. So which is it? That transposition, is it even or odd? Okay, well let's try and prove that it's actually odd. Okay? Now, so instead of doing it in terms